Welcome people to yet another Juddy Productions video. In today's video we'll be looking at Year 11 physics, how is energy from the nucleus utilised, our topic for today is mass defect, the energy calculation, and our skill is to perform the sample calculation. So we have in front of us on the screen at the moment a diagram representing the nuclear fission of uranium-235. So the process is as follows. A slow moving neutron is absorbed by uranium-235. It becomes a very unstable nuclear isotope of uranium-236, which proceeds to split or to undergo fission, producing a krypton-91 and a barium-142, two smaller but more stable nuclei. And in the process, it also generates 1, 2, 3 neutrons. Here's our nuclear fission equation representing the above diagram in a more symbolic manner. So let's have a look at some calculations of mass defect and energy. We're asked to consider the following nuclear fission reaction and associated data. So here's our reaction. So here's the reaction stated on the previous screen. So here's our mass of uranium-235. It has a value of 235.04395 AMUs, which is an atomic mass unit. The mass of a single neutron is 1.008665 AMUs. The mass of krypton-91 is 90.923445 AMUs. And finally, the mass of barium-142 is 141.9164534 AMUs. Now recall, one atomic mass unit, also known as a Dalton, is equal to 1.660539 by 10 to the negative 27 kilograms. And an AMU is defined as the average mass of a nucleon in a carbon-12 nucleus. So we have two tasks for today. Task number 1 is to calculate the mass defect, and task number 2 is to calculate the energy generated from the mass defect. So task number 1, calculate the mass defect. First of all, let's find the total mass of reactants. So that equals the sum of the mass of the uranium-235 and the mass of the single neutron. We add them together and we get a combined mass of the reactants of 236.052615 AMUs. So there we have the mass of our reactants. Now let's look at the mass of the products, as we have highlighted blue. The mass of the products is the sum of the mass of krypton-91, barium-142, plus 3 times the mass of an individual neutron. We add our totals together, and we find the mass of the products to be 235.8658934 atomic mass units. So we now have the mass of reactants, and we have the mass of products. You'll notice there's a slight difference. The mass of the products is slightly less than the mass of the reactants. The difference between these two masses is what we call the mass defect. So the mass defect is equal to the mass of the reactants, take away the mass of the products. So in this case, we have a mass defect of 0.1867216 AMU. Now if we take that value and we multiply it by the mass of a single atomic mass unit, that being 1.660539 by 10 to the negative 27, we find the mass defect for uranium-235 undergoing fission, producing krypton-91, barium-142 and 3 neutrons, to be 3.100585 by 10 to the negative 28 kilograms. That is our mass defect for the above equation. Step number 2, we're asked to calculate the energy generated. So E equals question mark. M is our mass defect, 3.100585 by 10 to the negative 28 kilograms. And C, as we know, is the speed of light. It's a constant. It has a value of 3.0 by 10 to the 8 meters per second. Using Einstein's energy mass equivalence equation, E equals mc squared, we can calculate the energy generated in this reaction from the mass defect, that is the mass lost. So we take our mass defect and we multiply it by the speed of light squared. That results in a mass of 2.7905265 by 10 to the negative 11 joules. Now we were asked to calculate the energy generated from the mass defect in mega electron volts. So first of all, let's convert our energy in joules to electron volts. Now electron volts are a very small unit of energy. So to go from joules across to electron volts, we have to divide the number of joules by 1.6 by 10 to the negative 19. So let's do that first. So we take our energy in joules of 2.7905265 by 10 to the negative 11 and divide it by 1.6 by 10 to the negative 19, and that gives us an answer of 1744.07906 electron volts. Again, we're asked to calculate the energy in mega electron volts, so we now need to convert electron volts into mega electron volts. To do this, we take our energy in electron volts and we divide it by a million. That is 1 by 10 to the 6. Effectively, we're moving our decimal place 6 spots to the left. So when I take the 1744,07906 and divide it by a million, I end up with an answer of 174.407906 mega electron volts.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.